Check, check.
Check, check.
Okay, do we have sound? All right, lights, camera, action. Good morning, everyone. Welcome back. Chem 1 from Berkeley, California. Just a week left of this, and we get to take the final and be done with Chem 1. We posted your midterms. You saw the announcement, posted the midterm scores, and we separated things out a little bit. And as a couple of you pointed out, there were some, well, we knew about a couple of the display problems and with B courses that you couldn't get to the right answer, or there were too many answers displayed. So we'll take care of all that stuff. And there were two questions that just weren't that exactly clear, and a couple of people pointed that out. So we'll give you guys credit for the explanations that you gave us. So a regrade will happen. It'll just do automatically. We'll just push a button. No one's grades will go down. So don't worry about that. We'll just give people a point. So that'll happen probably this afternoon or tomorrow morning after I look at all the emails that have come in and decide exactly how to handle it. So look for that before Monday. As far as what we have been talking about, we've moved through our discussion of acids and bases. And so far we know this. An acid is a compound that's in water or anywhere, but aqueous solution is where we're most important, donates a proton. So it has a hydrogen bonded to it somewhere. That hydrogen bond can dissociate. So it can take the H plus ion, the proton, leaves the molecule, leaves behind a negative charge on the larger molecule. That proton resides on a water. It becomes an H3O plus. The concentration of the H3O plus in solution tells us the pH. It tells us the acid strength of the solution. Acid strength of the solution goes by the concentration of the acid that you put in and the strength of the acid that you put in. Stronger acids dissociate more. Their protons are removed more readily. They're willing to get rid of that proton. It's basically a game in solution of who gets the proton. Does it end up on the water? Does it end up on that molecule? If it ends up on the water, then that's a strong acid. If more of it ends up on the molecule, that's a weak acid. The cutoff, basically, is the free energy. So when K, for the dissociation, for the proton leaving the acid, when that K is greater than 1, if it's spontaneous, so delta G for that reaction is negative, then that's called a strong acid. If delta G is less, if that's not a spontaneous reaction, then that's a weak acid. But remember, not spontaneous does not mean does not happen. Not spontaneous just means K is less than 1. So our cutoff for weak, strong acids is K bigger than 1. That's a strong acid. And assume it totally dissociates. All of the protons come off. The weak acid case is the one we're going to talk about in more detail today, where K is less than 1. So the equilibrium lies towards the associated form. A few protons come off, and the solution will get acidic. You'll notice a change in the pH. It won't be as dramatic as a strong acid where it entirely dissociates. So we'll look at those now and how those the difference between weak and strong acids and bases. So first, this is a situation where NH3 here is acting like a base, and all these things that I've talked about equally apply to the acid and the base. If it's the base case, then that base can remove a proton from water. And if it removes a proton from water strongly, then it's a strong base. And if the K is greater than 1 for that situation, that happens to completion. It's a spontaneous reaction. All the K is bigger than 1, we kind of lump into one category and say those go all the way. If it's a weak base, like NH3 here, then this has an equilibrium constant associated with it, which is less than 1. This is not a spontaneous reaction. Delta G for this is positive. The standard state free energy difference for this is positive. That does not mean it doesn't happen. It just means the equilibrium favors the reactants at equilibrium. It's a base, but it's not a very good one. So it takes some protons off. Most of it stays here as NH3, but it makes some NH4 plus, and more importantly, it makes some OH minus in solution. And the OH minus solution will affect the pH. So we'll detect that as a basic solution. So these come in pairs, as we've talked about before. So this ammonia NH3 acting as a base to form the ammonium ion NH4 plus. The K for that reaction is 10 to the minus 5. We can do this for anything. So we were taking the P of something. If we write P in front of it, that means minus log of that number. So minus log of that number, we mean it's something like the exponent. You have to take the minus log of both numbers, that one and that one. But it's about 5. It's the opposite sign of that exponent. This 1.8 makes it a little less than 5. But you can estimate if you said, well, the KB is 1.8 times 10 to the minus 5, you'd say, well, the PKB is around 5, and you'd be right. And if you saw the PKB of 4.7, then you would write down, well, then KB is 10 to the minus 4.7, which equals 1.8 times 10 to the minus 5. So we're just going to play that same P is PKA is minus log base 10 of K, B or Ka, whichever one we choose. And that's how we'll get these pKa and pKb numbers. pKa if it's an acid, pKb if it's a base. So here we are having the weak acid react with water. So that's the conjugate acid of this base. So we're writing it now reacting as an acid. So we're just saying, well, what if we put this in solution, in water solution, this NH4 plus? Notice this isn't the reverse of that reaction. This is, say we started with NH4 plus Cl, the ammonium chloride, and put that in. So we got these ammonium ions apart from this reaction going. Well, that would act as a weak acid, and you would form some of that conjugate base, and that proton that left the NH4 plus ends up on a water molecule and makes an H3O plus. If we take the minus log of that concentration, we get the pH. To get the pH here, we have to use the fact that that concentration and that concentration, H3O plus times OH minus in water, is always 10 to the minus 14. So if we know one of these, H3O plus or OH minus, we always know the other one. So we can always get to the pH. The Ka for that is 10 to the minus 10. So the pKa is going to be around 10, 9.3. So weak acid, weak base. And you notice they're both weak by our definition of weak. They both have Ks that are less than 1. So this is quite a weak acid. 10 to the minus 10, that's an abysmally poor acid. This is a better base. But that kind of makes sense because we say if you have a base, it's the stronger the conjugate base, the weaker the conjugate acid. And you can see that happening here. There's the base, there's the conjugate acid. This one is the stronger. It has the bigger K. And the conjugate acid has the smaller. It's the weaker base. So we see those things are going to be linked. Let's just talk through this. Which of the following has 0.1 molar solution has the highest pH? So now we're going to put these things in solution. Oops, this is coming a little early. I think there's a slide out of order here. Stand by. Where are we? Why do I see that? I want to do, I think I want to do this first. Let's do this first. Let's talk about the conjugate acid base pair. We just talked about the conjugate base acid pair. So here I'm going to write the same thing down, except I start with the weak acid case. And here it's that weak acid acting like a base. So here's the conjugate acid reacting with water. Here's the conjugate base reacting with water. Whenever you have one of them, the conjugate acid or conjugate base in water, both forms are there. They always form some equilibrium. So you'll always find them in pairs in solution, and you'll write the equilibrium expression. This is an acid dissociation. That proton ends up on water. You get H3O plus and AC minus. The equilibrium expression looks like this. We can write that already. Notice it's products over reactants. Water is a reactant, but it doesn't appear in the equilibrium expression. So we have this K. We call it a Ka because it's an acid dissociation. And AC minus, the conjugate acid base pair, appears in the equilibrium expression. So both of those are going to appear at some concentration in the solution. If I write this expression for the conjugate base, say I put that in water first, well, it's going to accept protons. It's a weak base. It'll make some of the conjugate acid. and OH minus ions. And you'll be able to write a Kb. You'll be able to write the equilibrium expression for that reaction. If you do that, you'll notice if you multiply the two, Ka times Kb, then everything cancels out except the H3O plus and the OH minus. So that HAC cancels that AC minus cancels that. And what you get is Ka times Kb for a weak acid base pair is that equilibrium expression for the water dissociation. We know what that number is. The product of those two numbers in water everywhere, wherever water is present at 25 degrees, anywhere, that product is locked at 10 to the minus 14 kW. And that you can see links the weak acid with its weak base. The interplay between these two tells you why a weak acid has the weaker the conjugate acid, the stronger the conjugate base, because those Ks are linked together. When one gets bigger, the other gets smaller. They're linked by Kw, the autoionization of water. Autoionization of water is 10 to the minus 14. I don't know why I didn't put that up there, so I'll do it now to remind us. This is 10 to the minus 14. So that means Ka times Kb has to be 10 to the minus 14. And you can see it there. That means that's about 10 to the minus 5. That's about 10 to the minus 10. That's about 10 to the minus 14. You take the actual product, it will be 10 to the minus 14. And the pKa and the pKb we can calculate as well. So the pKa for this weak acid is 4.7. If you know your logarithms, this is just minus log of this. If the Ka times the Kb is the Kw, which is 10 to the minus 14, that means the pKa plus the pKb must be 14, minus log of that. You add logs, you can add the exponents. So 4.7 and 9.3 add up to 14. The two acid and conjugate base. So let's go back now and do that chem quiz that we were posed here a second ago. Which of the following solutions has the highest pH? Oh, that's interesting. I didn't know I could do that. I can change the slide and leave the annotation on the board if I change the slide over here. Sorry, you probably saw me looking at that puzzled because I changed the slide and I saw the annotation stay there. So which of these following solutions has the highest pH? Let's talk through this together. We have a sodium acetate, NaAC minus. And remember, this AC minus ion, this acetate ion, it's acetic acid. I just am not writing out the entire formula for acetic acid. We'll do that in a minute. I'll show you what it looks like. NH3 and NH4Cl. Which has the highest pH? Now, you've probably been saying to yourself, well, Mark, you say I can put this acid in solution, or I could just put the conjugate base in solution. Well, how do I do that? How do I get the conjugate base? Just that, without the conjugate acid. Well, this is how you do it. You take the salt, the sodium salt of the conjugate base. So sodium acetate, and you should be able to do this all the time now. All sodium salts, all of them, dissociate completely. So if you have something called sodium acetate that dissolves in water completely to sodium salt and gives you the sodium ion and the acetate ion, AC minus. We don't know what that looks like, but we know it's a weak base. It's the conjugate base of acetic acid, HAC. So sodium acetate makes that. Same thing here. All chlorides are soluble. So if I take NH4Cl solid and I put that in solution, that gives me NH4 pluses, and these are aqueous now. I could write that down, plus Cl minus aqueous. These are all the aqueous ions. We don't generally write that down. We get tired of writing aqueous. If you see an ion in solution, we're not going to write the aqueous. Just takes too long. So those are the ions in solution. If you put the ammonia in solution, and we saw we could do that, ammonia gas, we could just dissolve it in solution, that will react with water, this NH3. These things dissolve, and then these things react with water. Sodium and chloride do not do anything. They don't precipitate. Sodium ions and chloride ions, salt totally dissociates in water. So that means the reverse, sodium and chloride ions coming together wouldn't do anything. We're not mixing these solutions. I'm just writing them up there. So what we have to deal with if we put that solid in water is we have to figure out what this does, and we have to figure out what this does. And of course, we're going to put the NH3. So we're going to put the NH3 in another beaker. We can take the NH3 gas and make NH3 aqueous. And that, we have to figure out what that does. We know that's a weak base. That's its conjugate acid. That's a weak base. HAC is its conjugate acid. So let's go through what those things will do. So we can guess that that solution and that solution will be basic because we've been calling them bases. That's a weak base and that's a weak base. We can guess that maybe this one will be acidic because we were calling NH4 plus a weak acid. So we have some guesses. NH3 in water, we know does this, and we know the K for that. It's a small number that doesn't want to appear on the screen. 10 to the minus 5. Once we have that AC minus in solution, that's a weak base. That also takes protons from water and forms OH minus. It's a miserable base. 10 to the minus 10. Hardly does this at all. It likes to stay over here as AC minus. Then we had the acid, NH4Cl. We put that in solution, and we have to worry about the NH4 plus ions. And those, that's a weak acid, donates a proton to water, forms that weak base, and H3O plus. And the question is, what are the relative pHs? I think, what was the question? What's the highest pH or lowest pH? And we have a K for that reaction as well. So this is a very weak acid. This is a very weak base. And this is a mid-range weak base. So the largest Kb has the largest OH minus concentration between these two. So NH3, if you put that in solution, it'll make some OH minus. This will make some OH minus, but the NH3 by far makes the most. It's 5 orders of magnitude better base, has a larger K. So the largest Kb is the largest OH minus. That will give you the highest pH. Is that what we asked for? Highest pH. Okay. Highest pH is so pH as well. How would I get the pH? Well, if I knew the OH minus concentration, I would say, well, I know OH minus Oops. Go back. I would say I know an OH minus concentration. I would get the H3O plus concentration by using H3O plus times OH minus is 10 to the minus 14 kW, and calculate the H3O plus and take the minus log of that. The larger this is, the smaller the H3O plus concentration is, and those smaller H3O pluses are what give us those higher pHs. Okay? And we just saw this a minute ago when we were discussing the size of those Ks. So there it is, the expression. Once we know an OH minus, we can get an H3O plus. Those things are locked together in solution. I think we're going to see this now again. So this was the acid. Animations are acting a little funny this morning. So this is the same slide, just reflecting now of ammonia and the ammonium ion. We had acetic acid and the acetate ion. So we had the conjugate acid base pair, and now we're saying this is a conjugate base acid pair. The conjugate base is the stronger in this case. And just coincidentally, these numbers are kind of mirror images of each other. So we had the Kb for NH3 is about the same magnitude as the Ka for HAC, for the acetic acid. So they're just a coincidental Ks of the same magnitudes. Okay, so for the acids HA1 and HA2, we have a pKa1 that's less than pKa2. So which is true for the reaction of HA1 in solution with the conjugate base of HA2, A2 minus? This equilibrium between their relative acid and base forms, to which side does that lie? Or are we in an equilibrium where there's equal concentrations of all of them and would have a K equal 1? So talk about that for a minute in your small groups, and we'll take a vote. let's come back and see what you're thinking. Take a vote if you haven't so far. Take a stab. We're equally split between A and B. A and C. So let's see. Let me give you my thinking on this. This is the reaction we're interested in. We want to know if it favors this side or this side. We want to know if there's a battle between the protons. Does HA1 get rid of its proton? It's the hot proton. You take it, I'll take it, you take it, I'll take it. Does HA1 give it to HA2 and HA2 stuck with it? Or is HA2 better at giving it to HA1 and HA1 is stuck with it? So it's the hot potato problem. Where does it land? The equilibrium constant tells us, if we knew the equilibrium constant for this reaction, if the products are favored, K is bigger than 1. If the reactants are favored, K is less than 1. So we have some information to tell us how that will work, but we saw that the pKa1 is less than pKa2. So we know something about the relative strengths of the acids. We know something about the strengths. In fact, we know their Ks. We know the equilibrium, pKa, and we know Ka and Kb. So we know how strong the acids are relative to each other. We can write that down. I should do that because I know everybody is bad at logarithms. So Ka is 10 to the minus pKa. pKa is minus log base 10 of Ka. That base to that power has to equal that number. So 10 to the minus Ka has to equal Ka. 10 to the minus pKa is Ka, if pKa equals minus log base 10 Ka. Those are the relationships you have to take to the bank. So if you know the relative size, so pKa less than pKa1 less than pKa2 means, since there's the minus sign there, that the Ka1 is bigger than Ka2. And Ernesto and I were just talking about it. We were saying, well, let's just throw two numbers in there. If this pKa were 3 and this pKa were 4, that was bigger than that one, then the Ks would be 10 to the minus 3 and 10 to the minus 4. And yes, 10 to the minus 3 is bigger than 10 to the minus 4. So A is the stronger acid. It's better at getting rid of its proton. So you would guess then, if it's better at getting rid of its proton, H1 is the stronger acid, that this equilibrium would lie to this side. It's better at getting rid of it. And you could actually derive that. You could take the two reactions with water, flip them over, and add them to get this, multiply equilibrium constants together, and you would find K is bigger than 1. That's a good exercise to go through. Okay, so for the acids HA1 and HA2, pKa1 is less than pKa2, same conditions. Which is true for this reaction? Now, I'm going to ask you about that thing that I just told you could do. That is, you could predict the size of that K that we just said was bigger than 1. And you could write it in terms of the Kas for the two acids. So let's go through that one together. So there's HA1. It has a K of Ka1. Here's HA2. It has an acid dissociation constant Ka2. What I want to do is write this reaction like this. So what I've done here is I've just reversed that reaction. I've said HA2 plus H2O goes here. I've reversed the products and reactants here on the bottom. If I reverse the products and reactants, I have to invert K, get the products and reactants back in the right order. And then if I add those two together, I get the reaction I've been talking about. HA1, HA2, then the H3O pluses and the H2Os cancel out. So that tells you if you put these compounds together, if you mixed a solution of HA1 and HA2 together, this is the equilibrium that would matter. These other things would cancel out of the equilibrium expression. Water wouldn't appear in the equilibrium expression anyway, but the H3O plus concentration would cancel out of the equilibrium expression. There can only be one H3O plus concentration in solution. So that has to be the same if both those things are in solution. So, but you know already, because we went through this with equilibrium constants, if I add two reactions, I multiply the equilibrium constants. So I take the product of those two things. So the K for this reaction is the product of the first and the second. So it's Ka1 over Ka2 is that reaction. And that is the combination, as you know, that would give you a Ka bigger than 1. You have to put the bigger K on the bottom and the smaller K, or the bigger K in the numerator and the smaller K in the denominator to get a number bigger than 1. This number would have been less than 1 because both Ka1 and Ka2 are less than 1. So that one was out. And the product of them, both less than 1, would have been less than 1. So you could have, since you knew K was bigger than 1, this was the only one that could have been bigger than 1 anyway. So you could have done it that way as well, just because you knew their relative magnitudes. So here we have some solutions of weak acids and weak bases, and strong acids and strong bases. So HCl and sodium hydroxide, NaOH, HCl, hydrochloric acid, HCl. That's a strong acid, K much bigger than 1. That's a strong base, K much bigger than 1. Here's acetic acid that we've been talking about, HAC, weak acid, K less than 1. NH3, weak base, the dissociation constant less than 1 for that. Liquid water in the middle, 5 different solutions. And here are their relative pHs if they're about 0.1 molar in concentration. If they're about 0.1 molar, if you put HCl, 0.1 moles of that in 1 liter, HCl completely dissociates. Every proton ends up on a water. So that means you have 0.1 molar H3O pluses. You have 10 to the minus 1. So if these are all, we'll go through this ad nauseum because I think it troubles people. HCl totally dissociates into H pluses and Cl minuses, 100%. So you get all your H pluses. So if I start out with 0.1 molar, 0.1 moles per liter of HCl, it gives me 0.1 molar H pluses. So my H plus concentration, or H3O plus concentration, same thing, is the H pluses are all on waters. They're not there by themselves. H3O plus and H plus concentration, I'll be lazy, write those as the same thing. H plus concentration or H3O plus concentration is 0.1 molar there. If the HAC concentration, I put in 0.1 moles of HAC in 1 liter, the H's don't totally dissociate. So you get less than your H plus concentration here is going to be less than 0.1 because this doesn't totally dissociate. So we get the pH exactly here because this is 10 to the minus 1. So minus log of 10 to the minus 1 is 1. So that's the pH. Here, we know the pH, the H3O plus concentration is less than 0.1. If that's the pH, we know what it is. The pH, the H3O plus concentration is 10 to the minus 4. That's what the pH is. 10 to the minus pH is the H3O plus concentration. Here, the H3O plus concentration is 10 to the minus 7. Here, the H3O plus concentration is, it's not 10 to the minus 10, because this is, well, I'm sorry, it is 10 to the minus, the H3O plus concentration is 10 to the minus 10. That's the pH. It's very small. So here it's 10 to the minus 10. It's very small because this is a base. It's forming the base. Here, H3O plus concentration 10 to the minus 13. That's because the OH minus concentration in this last one, we know since that's a strong base, that 100% dissociates and gives us OH minus in solution. That concentration is about 0.1. And if that concentration is 10 to the minus 1, then the H3O plus must be 10 to the minus 13 because the product of those two, H3O plus and OH minus, must be 10 to the minus 14 if they're in water. So we understand all those numbers. We understand why this one has the higher pH, or excuse me, the lower pH than this one, because that's the strong acid, that's the weak acid. We understand why this has the higher pH, strong base, weaker base. So what about their conductivity? What if you do the bright light thing and put it in, put your little conductivity bright light meter in there? This, lots of ions because it totally dissociates. This dissociates less, so fewer ions for the same amount of HAC as HCl, so a dimmer light. This, we know, pure water, barely any light at all. The weak base, same situation, some ions, and then for the same concentration or for the same amount of base added, a brighter light. So lots of ions, fewer ions, no ions, few ions, lots of ions. So the ionic strength, the brightness of the light, we can also talk about. So let's mix them together. Let's take solutions 1 and 5 and mix, and let's ask what is the pH at the end and what is the light at the end. So I have 3 options. Just the qualitative, is it acidic, neutral, or basic? Bright light, dim light, no light. Let's talk about that for a second, and we'll take a vote. Let's see what you're thinking on that. Take a vote if you haven't so far. We're thinking neutral. About 80% of us think neutral. And yes, it's neutral. You mix an equal concentrations of strong acid and strong base. That's your gut feeling, and your gut feeling is right in this case. That's a neutralization reaction. That's going to be neutral. What about the brightness of the light? Let's do quickly. We'll just take 30 seconds and tell me how bright the light is going to be when you stick it in that mix. So vote on the second one, bright light, dim light, no light. Oh, for goodness sakes. In the middle of lecture? No, not right now for sure. Send them that.
He asked if I could stay
Oh.
on after class.
Okay. Here we are, guys. This one we just wanted to take a stab. Do you think the light's going to be bright, dim, or off? Let's see what you're thinking. Most of us think dim or off, C. About 65% of us are down here. The other split here. Well, let's watch the demo. Let's watch some guy do it. There's probably somebody has done this. Oopsie. So if we can go to the board here, Sydney, I'll start this YouTube. We'll watch the reaction happen. So I have the solutions of the strong acid, HCl, and the strong base, NaOH. The color will tell us the pH. So it's going to be yellowish, which means neutralish pH. So the blue and the pink, you didn't see the blue and the pink, they were quite fast, went to yellow. That's the indicator. So that's very close to the water pH. So, but the question is now, we'll let's watch this guy talk about it. He's going to say, oh, if you mix HCl and NaOH, you get you get that H with those OH minuses making water and NaCl. The NaCl still ions in solution, which is going to help us answer the second question. So stick the light bulb in. We can take the light bulb and stick it in there. And you guys were saying dim or off. And the answer is no, bright light. Bright light. Why is it bright light? Well, it's bright light because that's what happened. And I'm sure I must have the animation. I'm probably using the same slide. Not using the same slide. These have been gone over a million times. This one looks very similar though. What happened? Uh-oh. What happened to the oh no. What happened to the oh goodness, PowerPoint. There it is. So what happened there? Well, this is the reaction that happened. All these, let's see what the animation is here. That's not very helpful. All these H pluses found all those OH minuses and formed water. And the K for that is 10 to the minus 14. or 10 to the plus 14. I'm going in that direction. H plus, OH minus, going to H2O. K for that is 10 to the plus 14. All the way that way. You have pure water, essentially. All the OH minuses and the H pluses find each other and make water. That's why it's neutral. But that leaves behind the Cl minuses and the Na pluses. I've written them together there, but that's sodium chloride. That's just salt. That stays as ions. That doesn't become a solid at the bottom. That stays as ions. And that's very conductive. And that's why you get the bright light. So you go, bright light. Do you guys recognize, if I go, bright light, does that like a movie line that resonates to you guys who are much younger than me? No. Okay. What is it? The movie's even a little before my time. I'm trying to remember what it's called. Gremlins. The movie is Gremlins. They're these little tiny, look like furry stuffed animals. I think it's a early Steven Spielberg movie or something. Gremlins are these cute little living stuffed animal things. They're adorable. They hate bright light. So when they see bright light, they go, bright light. And if you feed them after midnight, they turn into horrible little creatures. So you have to not feed them after midnight, and they're afraid of bright light. Google that, Gremlins. Very old movie. So let's see if we get bright light or dim light on the next one. So now I'm going to mix 2 and 4. So 2 and 4 are the weak acid and weak base. So let's go back. I just wanted to write on the board here. So just to remind you, and you have the slides in front of you, hopefully most of you, but so this is the HAC, and this is the NH3 solution. So the weak acid and the weak base, we're going to mix together. And what's going to happen there? So we'll talk through the first part together. See if I have the animation here. So this is the reaction that's getting ready to happen in solution. That plus that goes to that and that. And you have to say, does that produce a neutral-ish solution? Well, we've done this already. We've mixed things that can react together. I have the Ka for this and the Kb for this, and they are just coincidentally, as I said, about the same size. So this is about the same strength acid as that is a base. So they indeed go to a rather neutral solution, simply because if their acid-base strengths are different, then you would expect one to win out over the other, and you'd have a slightly acidic or slightly basic solution. They happen to be about the same. The question is, what about the light? So let's look at the experiment for the light. Okay, it looks like I've mixed them together, NH3 plus HAC minus, and we can see that it's a neutral solution. So we'll begin the playback there. So the color told us it was about neutral. There's a pH indicator. The pink was acid, the bluish was base, yellowish was neutral. And we have those Ka and Kb at about the same magnitude. Okay, talk about that. Gives us about a neutral solution. Equal strength acids and bases. What about the light? So we're trying to decide now, are all the ions used up? Or are all the ions in solution? The answer is, ready? Dim light, no light, and bright light. Bright light again. There's still lots of ions in there. What ions are those? Well, I think you can probably guess. Oops. Sorry. I need you to stop. Stop. And get small. You guys probably wish you could do that to me all the time. Where's the off button? So why was it a bright light? Well, oh, do I not? Yeah, we'll talk about mixing the acids and the base here. So here's the acid, and so I had HAC, H3O plus, and AC minus. That's Ka1. We were talking about this base here, but I've actually written the Ka reaction down there. So the Ka for that weak acid, whose conjugate base is here, is Ka2. And we've done this before. We've written together two a weak acid and a weak acid reacting to each other and decided who got the proton. And we said, well, if you're the stronger acid or you're the stronger base, the stronger acid gets the proton, the stronger base doesn't. In this case, those two things were about equal. So these things get to some equilibrium equilibrium where the NH4 plus and the AC minus concentrations come to an equilibrium at around pH 7. What about the ions left over? Well, I'm going to write this one as NH3 plus H3O plus goes to NH4 plus plus H2O. That's 1 over the Ka again. Oh, shoot. Well, I'm going to add them together. Not sure why that line is up there. I'm going to add them together, and I'm going to get AC minus, NH3 plus. The H3Os cancel out, and the H2Os cancel out, and gives me NH4 plus plus AC minus. And the question is, what is the size, relative size of that? And again, the K is, so it's the Ka1 of HAC, it's the Ka2 is NH4 plus, and we can go back and look at that, and we remember Ka for the HAC was 10 to the minus 5, Ka for the NH4 plus was 10 to the minus 10, so that number is, well, for goodness sake, that number is ginormous. 10 to the minus 10 in the denominator comes up as a 10 to the plus 10. So this number is like 10 to the plus 5. So that says this reaction lies all the way over here, and those ions are strongly in solution, and you get a bright light. Okay? Oh, goodness. So, okay, there's just the solution again, bright light. Okay, just looking at the time there. Let's do a calculation. Sometimes it's helpful to you if I do a calculation and work it out. So the salt of hydrocyanic acid, HCN, and HCN has a pK of 9-ish, and formic acid, so I'm talking about the salts, not the actual acids themselves. Formic acid, CCOOH, has that pK, are prepared in 0.1 molar solutions. Calculate the pH of the less basic solution. So we can get the Ks. The Ks are 10 to the minus pKa of each of those acids. So the Ka for HCN and the Ka for the formic acid are 10 to the minus 9 and 10 to the minus 3.75. Those are the relative numbers. We could actually put that into our calculator and get a number. that doesn't have a fractional exponent if we want. We don't have to do that. We can work with fractional exponents, but there it is. If I do that, so Ka, you can see that HCN is quite a horrible acid, 10 to the minus 10. This formic acid is a reasonable acid. It's a weak acid. K is less than 1, but not a horribly small number. Formic acid is the acid that present in ants in their stings. So that's common in nature. I can get the KBs, and I actually want the KB, because if I take the salt of hydrocyanic acid, that's the conjugate base. That's NaCN. So I want the KB. The KBs I can get because Ka times Kb is always Kw, and pKa plus pKb is 14. So I can get the Kb for the conjugate base, Cn minus, simply by doing that math. 9.31 plus 4.69 equals 14. And I can do the same thing for the formic acid. So this is sodium formite. If I was talking about the salt of the conjugate base, sodium cyanide, if I was talking about the sodium salt. So I have those two numbers. So the Cn minus is the better base. So it has the smaller pKb, and we would have expected that because we saw the relative conjugate acid strengths. So the less basic solution comes from the worse base, in this case, the formic acid solution. So let's do that concentration. I'm going to take formic acid. I'm going to get the Kb, 10 to the minus 10.25, which is that number there. And I'm going to say, well, if I took that sodium salt, sodium formate, and I put it in water, I would make sodium formate. That will react with water, the formate part. So I'm going to take that. This reaction goes 100%. That's just a sodium salt dissolving in water. That goes 100%. And then this stuff reacts with the water because it's a weak base. And we know it's the weaker of the two bases. We just went through that argument. So that in equilibrium with water, I can write that down. I know the K for this reaction. It's that. So if I know the K for this reaction, I can go through my icebox calculation, say, well, if I started out with 0.1 molar of that and none of this and this, 0 concentrations of those two things, a little of that dissociates, some small amount. For every X molar of that dissociates, you'd get X moles of that and X moles of that. The equilibrium concentrations then are the difference between those two things. 0.01 minus X, X and X. So you set that equal to the equilibrium expression. Products, X times X over reactants, 0.01 minus X. And because that K is very small, X is very small compared to 0.01. So you can neglect X in the denominator there, and you can say very simply, X is going to be the square root of that number. So something like 10 to the minus 6. Square root is half the exponent, something like 10 to the minus 6. That's the OH minus concentration. So if the OH minus concentration is 10 to the minus 6, the H3O plus concentration would be 10 to the minus 8, because those products, H3O plus times OH minus, not exactly that because there's that 2.37, but the pH is going to be something like 8-ish, 7.5, 8. If we do that exact number, so let's go ahead and do that calculation. H3O plus times OH minus is 10 to the minus 14th. Always true in water. So H3O plus is this. We can do that number, and we'll get that number, and we're going to get that number around 8 that we expected to get for the pH. Okay? So go through that solution. I think I put that in your slides or in the handout. If I didn't, you can take some screenshots or just email me and I can put it in the handout. But that's so common. You'll see that calculation in the reading. All those reading links I gave you, they do those calculations for you. So let's do a little more titration. So we've talked about this process of adding acids and bases together and using up the acid. So we did it for the strong acid last time. We said, what if it's just a strong acid and you titrate it with a strong base? What about the weak acid, weak base solution? Those are the interesting ones. It turns out strong acids, they're the spontaneous ones. They have the big Ks. It's exciting, but then it's over. A lot of things like that. The weak acids, they hold back. They don't dissociate all the way. Those are the interesting ones. And those are the ones that commonly form in nature, and they're the ones in our bodies that we're interested in knowing more about if we're interested in biological chemistry. So here's a titration curve, and this is titrating an acid, and we always titrate with a strong substance. So we're going to titrate a weak acid with a strong base because we don't want to have too many complications there. So we're going to take HA in solution, react it with a strong base, form water. It's going to take the proton away, and the A minus. Now notice that is not the acid-base dissociation reaction. The acid-base dissociation reaction is HA reacting with water. It's the base reaction. It's the conjugate base reaction. I've written in reverse there. This is the reaction that we're interested in happening, though. HAs are present in solution. I'm adding OH minuses. I'm interested in what's happening between those two things. And coincidentally, it's the reverse of the conjugate base reaction. That's going to help us. So let's start at point A. At point A, well, we can talk about several points, A, B, C, D. At point A, we just have HA in solution. At point B, there's a mixture. At point C, we've added a mole of acid for a mole of base for every mole of acid that we had. And then here at point D, we've overwhelmed it and we've added a lot of OH minus. Those are the basic points in our titration curve. So between HA and equivalence point, so we start out with mostly HA. And if it's a weak acid, it really is mostly HA. This doesn't dissociate very much. So you got lots of this. Every OH minus, though, converts it into an A minus and water. So as you add these OH minuses, as you add the strong base, this concentration, HA, goes down, the A minus concentration goes up. Somewhere in this region, there's a mixture of those two. Here it's mostly AHA. Here there's a mixture of the two ions. And then when you've added one of those, for every one of those that was initially there, so you've used up all those, at point C here, you have predominantly A minus. Now you never have all of that or all of that because they always are in equilibrium. So this will always go back a little and form this. And if this is there by itself, it will always get rid of some of its protons and form some of this. The equilibria are always in play, but if it's a weak acid, it's mostly this. And if it's a weak base here, it's mostly that. Okay? And weak acids and weak bases come together. So that's the general description of the titration curve. And when you get out here, it's just OH minus. It's that stuff that you're adding is determining the pH. This is the interesting part right here, where there's a mixture of the two. Strong acids and strong bases don't have this behavior. So we call that region the buffer region. That's the most important region, and we'll talk about that a lot. That's where a lot of your exam questions will be, because this is what affects biology, and most of you are interested in the biological sciences. So if you did it with a base and you titrated with a strong acid, you'd have the mirror image effect. You'd have mostly B, and then you'd have a mixture of B reacting with a strong acid to form the BH ion. So you'd have a mixture of the two at equivalence point. You would have converted all that to that. And then way out here, the pH is determined by all that extra acid you're adding. So here I've finally written down the structure of this acetate AC minus thing that we've been talking about this whole time. So it's acetic acid. You can see why I don't write it out every time. Too many symbols. So the abbreviation for that whole ion is AC. There it is, the acetate ion. It has just this one acidic proton, has lots of hydrogens. Only this one comes off. These on the carbon don't come off. This is an acidic proton. It can dissociate. Carbon-bound hydrogens don't dissociate in general in water. So that's an acidic proton. Oxygen-bound protons do dissociate in water. So that's acetic acid. That's the expression. What's the pH? Well, it's a weak acid. So at the beginning of the titration at point A, we expect the pH to be on the low end, the acidic end, below 7. But higher than 1. Why higher than 1? Well, if it's 0.1 molar acidic acid, it's a weak acid. If it were 0.1 molar strong acid, then you would have 0.1 molar H pluses, and that's pH 1. This is a weak acid, so it's not going to get that far dissociated. So that's what our expectation is. We can do the calculation. At equilibrium, I've skipped the whole ice box thing and just written the equilibrium concentrations. A little of your initial HAC dissociates. That small amount is X. I can write the equilibrium expression, set it equal to K, and we know the Ka for acetic acid. We've looked at it a couple times now. pKa around 4.7. Assume X is small, the usual assumptions, and you'll get an X, which is the H3O plus concentration. So the pH is going to be around 3. A little less than 3 because of that 1.3 there number. So 2.88 is the pH, minus log of that number, which is the H3O plus concentration. That we should be able to do. You guys, this happened so fast. We're in the fall semester. You've had like a week of practicing this already. You guys are probably just seeing it for almost the first time. So practice those calculations. We'll go through this together. The pH of a strong acid, HCl, is 3. What happens when you dilute it by a factor of 10? So you have HCl here. The pH is 3. Add water, dilute it by a factor of 10. Put your pH meter back in there. What is the pH? Well, pH scale goes by factors of 10. 1 pH unit is a factor of 10 in the concentration of, that's what log base 10 means. Every unit is a factor of 10. So pH 3 is 10 times as acidic as pH 4, 10 times the H3O plus concentration. So what we're saying here is we just went from pH 3, put in 10 times, we've diluted it 10 times, so the concentration went down 10 times. So now the concentration is 10 to the minus 4. The concentration went from, so we know, maybe I even have it in the animation. If not, I'll write it on the board there. If the pH is 3, then the H3O plus concentration is 10 to the minus 3. That's what that number means. If I dilute that by 10 times, then that goes to 10 to the minus 4, right? 10 times more dilute. 1/10 the concentration, initial concentration. So if that happens, initial concentration, dilute by 10, that goes down by a factor of 10, and you have 10 to the minus 4. What's the pH now? Well, it's 4. 10 to the minus 4 means pH is 4. It is 4. Okay. What about weak acids? Are they different? So a solution of HAC is pH 3. What happens if I dilute that by a factor of 10? Talk about that for a minute in your small groups, and we'll take a vote. Okay, let's see what you're thinking. Oh my goodness, we're all over the map. About equal, about half and 40%, 40% for A and B, and some people for C greater than 4. So let me give you my thinking on that. So exactly the same thing as last time. The pH is 3. So the H3O plus concentration is 10 to the minus 3 in that solution. You measured it. So that's true. Dilute by a factor of 10. Dilute by a factor of 10, and that concentration goes immediately to 10 to the minus 4. That's what happened in the strong acid case. So the question you have to ask yourself, is there something different in the weak acid case? And I think you know that there is. So in the strong acid case, you put in 0.3 moles of HCl to 1 liter of water. Those 0.3 moles all dissociated. It gave you 0.3 moles per liter. I'm sorry, 10 to the minus 3. You put a thousandth of a mole, 10 to the minus 3 moles of HCl in the water. They all dissociated. It made 10 to the minus 3 moles of H3O plus in your liter of water. And the pH was 3. Then you added 10 times the amount of water. You went up to 10 liters. And that concentration went down by a factor of 10. And there was nowhere else to get any more H3O pluses because the HCl totally dissociated. It blew its whole wad to start with. Done. We said the acids, strong acids are exciting, but then they're done. The weak acid, how did I get the weak acid to pH 3? Well, you know, a strong acid, you put in 0.3 moles, or I keep saying that wrong, sorry, 10 to the minus 3 moles of the strong acid. To get a weak acid to the same pH, you got to put a lot more. It doesn't totally dissociate. This is happening. And it doesn't happen very well, so you got to put a lot of that in to get to the same pH. So after you dilute this by a factor of 10, there's lots of this left. And you know what that says? Oh my God, I suddenly have more space. I suddenly have more water molecules. I am going to continue to dissociate. It's just like a gas that sees more volume. It expands into it. So immediately, I admit, I will tell you, as soon as you add the water, the pH will go right to 4. But then all these that are still left there will start to dissociate, and you'll have to get a new equilibrium. And that new equilibrium will add more H3O pluses to solution. And that concentration of H3O pluses will go up, and that makes the pH go down to less than 4. So the magic, the interesting thing of the weak acids is they have this capacity to not change their pH very much. That's what buffering means, that you resist change. The strong acid could not resist the change in dilution. You diluted it by a factor of 10. I have no more protons to give. The weak acid says, I have plenty of protons left to give. Go ahead, dilute you. I will give you more protons. And I will maintain that pH near 3 if I can. So we don't have to calculate what it is. We could calculate what it is, but it's less than 4 is what we know. We won't do the calculation today, but there's the summary. It produces more H3O plus. So the pH after it comes to equilibrium is going to be less than 4. Okay, that's the excitement of weak acids, such as it is. This ability to hold back, and that ability to hold back and give you more H pluses when you need it is what makes our bodies go, and what makes the buffered systems in our bodies work. So we're going to learn about that more next time. So I have office hours, so I will stay here for a few minutes if anybody wants to ask some questions. Andrew will bring you all back together in the Zoom, or type questions into the live chat, and I'll take some questions. Yes, sorry guys, we apologize. Amanda says there's the homework links aren't active yet. Yeah, we had miscommunication. We didn't get them all up yet. I'm gonna start working on that today. Hopefully by tomorrow afternoon, we'll have the homework for the rest of the semester up and ready to go. Sorry, you have nothing to work on, but there's not many people in the live stream. I should have said this earlier. Do the darn homeworks. Amanda, this is probably the Amanda who gets all the points. Amanda wants to do them because we're taking the, I don't know how to say this any more clearly. We are taking the homework problems and we are putting them on the exam. If you do the homework once, they're randomized. You might not, there are more questions. Do them over and over until you don't see any more new questions. That's the way to study for this class. Do the homework over and over and over. When you stop seeing new questions, you've seen them all. One of those ones you've seen might appear on the exam. Some of them will appear on the exam. Okay?
Do we have a definite midterm one?
No definite midterm one yet. So those of you that are stressed out, we're going to decrease midterm one. It's not going to be by a ton. Right now, it's 20% of your grade. I would say it'll probably go down to somewhere between 15 and 20. I haven't crunched the numbers, and I don't remember how badly it went. I think the average was about 10 points lower than we wanted it to be. Is basically what happened. So we'll reduce the percentage a little bit, so that the average on that first one was about the averages of all the other ones. The weightings do increase, though, as you know. The midterm one was always weighted less than the other two. That's how we do it. We give you a chance to break in and get better at this. So if you calculate your grade now and you're stressing out, make midterm one 15%. If you make it 20%, then you get the lowest possible grade you're going to get. When we make that lower and you did poorly, I mean, those of you that did great on midterm one doesn't make any difference to you at all if you've done the same on all of them. Okay? If you're doing the same on all of them, it doesn't matter what we weight them. So unless you're wildly varying and you got a really bad grade on midterm one, the number you're getting, the total percent, is going to be a reflection of your grade. I don't like talking about grades, so I'm going to stop. Go ahead.
One question from Tuesday from Swappy. I was just wondering how dissolving would be exothermic, because one would be forming more bonds with the water and so releasing energy. This is for CO2 dissolving.
Oh, good question. So the question is, when you dissolve stuff, I think she's saying, why shouldn't it always be exothermic or something? Because you're forming.
How is it exothermic?
How is it exothermic? That's a good question. So I think Swati's saying, well, something's dissolving and you're making associations between molecules. So if you're making associations, isn't that an endothermic process? Shouldn't the associations that you're making, that you had a gas and now it has some associations with water molecules, that making, if you're going towards attractive interactions, then that would be an endothermic process. So brilliant. Yes, I'm glad you're thinking about it that way. And I'll tell you, we only looked at that one example. So your intuition is absolutely correct. It's just, the world doesn't always perfectly follow our intuitions. The carbon dioxide dissolving in water is a very interesting problem. And anytime you dissolve something in water, it's a kind of an interesting problem, because you kind of expect, well, entropy should increase. You're dissolving things. But this case, there's a gas coming in to the liquid. Is entropy going up or down? And sometimes you dissolve a solid in water and you expect, oh my gosh, entropy has to increase, but it doesn't, because the solid makes liquid water has a little bit of order to it because all those hydrogen bonds. And some things you can dissolve in water and the entropy decreases. So all dissolutions in water, all bets are off. So your intuition is just often off in water is all I have to say to use Wathi. But yes, you are thinking along the right lines. Good question. It's just water. It's just water. Everything is weird is what it comes down to. Other things? Okay. Questions on grading and stuff. Ask your GSIs. They know what's going on. Remember, the general thing is midterm 1 will go down a bit, but calculate your grade. You've got the lowest possible grade you can get if you use the weightings now. 2, your midterm 3 is not completely finalized. You might get an extra point or 2 when we regrade it. No ones will go down. So you might go up a little there too. So the grade you calculate right now might be just a little below what you end up with in the end. Other things? Okay, guys. We'll see you on Monday. And by then, we will have all the homeworks up. And yes, do them. Oh, wait.
One last question from Lucille. Should we memorize some examples of strong acids and bases, or is there another way to figure out their strength based on their molecular formula?
Oh, Lucille. Lucille asks, should we memorize a list of strong acids and strong bases, or is there another way to figure out if it's a strong acid or a strong base? Good question, and it's a 2-part answer. So I don't want you to memorize anything in this class. As you know, I try to get that to a minimum. You had to memorize SPD, and you have to memorize VSEPR, tetrahedral, and some bond angles. I'm sorry, you just got to do that. I don't make you memorize any names of chemicals. I hate that. Even UC, even when I give you an element on the questions, I try to give you the symbol and the name so you can go find it quickly on the periodic table. So weak acids as strong acids. If I give you a K, it's a weak acid. Strong acids don't have Ks. We assume they totally dissociate. So the Ka doesn't matter. Okay, 100% dissociation. So if you see a K, it's a weak acid. I don't want you to memorize stuff, and I hope I remember to do this, but HCl, hydrochloric acid, is a strong acid. It totally dissociates. The only other one you would possibly see is sulfuric acid, H2SO4. That's a strong acid. NaOH, sodium hydroxide, the example we gave you there, strong base. But I'm not going to try and trick you or make it confusing because you don't know whether it's a strong acid or strong base or not. So by and large, you see a K, I give you a K value, or I'll say K is large or greater than 1. And that means it's a strong acid. So I'm being a little wishy-washy because I said that HCl you should know is a strong acid, but let me make it clear. I'll just tell you. HCl, a strong acid, is added to water. Remind me to do that, guys. We'll review the midterm and we'll make sure. Some semesters I have said to students, you have to know HCl. I usually tell them nitric acid, hydrochloric acid, and sulfuric acid. You have to know those. But this is summer. I will tell you. Okay? Other things?
Yes. For the ChemQuiz on mixing solutions 2 and 4, HBC and NH3, can we also use Ka or K equals Ka times AC times Ke times NH3 instead of K equals KAC divided by Ka?
Okay, somebody's typing a long thing into the chat. Is it plugged in? Okay. Just trying to read. For the ChemQuiz, so mixing 2 solutions, the weak acid and the weak base. Can you also use Short answer, Amanda, yes. There were a lot of ways to arrive at that. She's basically saying, can I use the ratio of the weak acid, weak base association constants, or the weak base, weak acid dissociation constants? And yes, as long as you end up with stand back here so you can see me. As long as you end up with the expression, you wrote two chemical reactions and you got the final chemical reaction. There are a couple different combinations of initial reactions that would give you that final. As long as you do your accounting right, then there are a number of Ka, Kb combinations that would give you the same answer. And that's the case because Kas times Kbs are Kws. So you can always mix and match Kas and Kbs and get to the same K for a given reaction. I think that's what you're asking. If not, tell me. Tell me, Amanda. I'm looking at the live chat. I don't know how fast. Are we done? Yes, thanks. You're welcome, Amanda. Okay, other things?
How do we know which salts completely dissociate? For example, you say sodium salts always completely dissociate.
Oh, good. That's another good question. Is that also from Lucille? How do we? Yeah. Lucille always wants to know exactly how much I have to know. So Lucille says, what about the salts that totally dissociate? I will probably just tell you that too. But you guys should just take one thing you can take to the bank in chemistry is sodium salts, all of them essentially that you will encounter totally dissociate in water. And chloride salts the same way. It's totally dissociate in water. But again, that's details. Summer goes too fast for you to memorize frivolous details. So I will tell you, sodium chloride, which totally dissociates in water, is added. So I'm making that deal with you. And you guys are all lucky because Lucille is enforcing the don't memorize anything rule. So she's working on your behalf. But yes, Lucille, in general, you should take home sodium salts are soluble and chloride salts are soluble. So because you'll use that in life later on, maybe. Do you have a question, Ernest?
For the titrations, are we supposed to assume that there's only one equivalence point? Because I think for like, I think it's H2SO4 or SO3, I think it has two equivalence.
Yeah, Ernesto here sitting in the room has a question. Will there be one equivalence point for titrations? Could there be two? And yes, there can be two, and we're going to talk about that on Monday.
For the bond energy question on midterm 3, what makes X2 plus 3Y2 reaction arrow to XY3 exothermic? I was thinking that because more bonds are being formed, it would be exothermic.
I think the number was delta H is a positive number for that.
Yeah, that's what I was.
For that reaction. So he's asking why it's endothermic rather than exothermic if you're forming bonds.
For the reaction number 1, where we gave them delta H is 250.
Yeah, actually.
Okay, so the question is, on the midterm, we gave you a reaction 1, and it was X's and Y's forming XY bonds. And I guess we gave you a positive delta H, so we said it was endothermic. It can be endothermic, it just depends on the relative values of the bonds. But you're right, we should have been a little more careful. I don't remember. So here's what we did with that question. This was an experiment. You guys were guinea pigs. I wanted to give you a question where we could put a bunch of different numbers in. Everybody got a different number, and then you did a bunch of calculations with that number. That was my grand experiment, and it worked pretty well. We all could do it, and then we could pull them out of B courses, and we could grade you on them. That was what I wanted to try to see if we could do, and we succeeded in that. But you're right, if they were real numbers, I mean, we made up these chemicals X and Y. If they were real numbers, then you would expect if you're forming more bonds, and that's a stronger bond, that should be an exothermic reaction. But we are making up these numbers. Okay, the number that you got for the XX bond energy was made up. So that's the short answer. It was a made up situation. So, okay.
This one might be a little more out of scope, but Swarthy wants to know, how do we know which hydrogen comes off? Like for acetic acid, why is it only the proton and the OH that comes off?
Yeah, good question, and we will talk about that more. So Swarthy asks, how do we know which proton comes off? It's really the best question in chemistry. Which proton comes off? In biochemistry, it might be the premier question. Which proton is going to come off there, because that makes so much difference. But the answer does turn out to be there are relatively few protons that can come off. Most bonds are pretty darn strong. You put them in water and they stay put. What we're talking about is bonds that don't stay put in water. So they are essentially a relatively weak interaction, and the reaction with a water molecule has some pull. There's enough free energy in exchanging that there's a significant amount of that present at equilibrium. Which one comes off, you won't be responsible for, but I will tell you, like I said a minute ago, and we will look at a few more examples of acids and their actual chemical structures next week. The candidates for the ones that can come off are the protons attached to the oxygens and the nitrogens, especially if it's attached to nitrogen and has a charge, then that's likely to come off. If it's attached to oxygen, it has the potential to dissociate. Not all of them, but you could say all protons are acidic on the whole molecule and just assign a Ka to every single one of them. And the Kas for the ones attached to the carbons are tiny, 10 to the minus 40. So they don't come off at all. The ones attached to the oxygens, 10 to the minus 5 or 10. The ones attached to the nitrogens, which is H plus and H plus, 10 to the minus 5 or 10. So that's the answer. Okay? Others?
Yes, Alex has a question. One of the midterm 3 questions asks about enthalpy. Don't really lack bond energy needed to solve this. The question, it was one of the reactions that XO3 minus plus Y2 plus 2.
Yeah, so one of the questions, so Alice is asking about there were 3 calculation questions on the midterm, 3 blanks you had to fill in. The first was just the XX bond energy, which was the number in the table. You just had to take the opposite sign, because I told you what's the bond breaking, and the number in the table was the bond making. I'm sorry. The first one was I'll shut up because I don't remember exactly what the question was. Alice is asking about the third one, which involved XO bonds with oxygen, and a YY bond breaking as well. And you were to calculate the enthalpy for that reaction. To do that one, you also had to calculate the bond energy of the YY. So you kind of had to do the one before that to do the second one. So in order to do the second one, which had XO bonds and YY bonds interchanging, you had to have already done the first one. And in general, no questions in the big scheme of things ever depend on any other ones. And that's still true here. I mean, you could have done that one by itself. You just would have had to do the first one first. You would have got the same number. So the answer is you can calculate that enthalpy for that reaction with X's, O's, and YY's, because you can calculate the YY from the other information that's in the table and the reactions. I think that's the question.
She says, don't they lack the bond energy of the OH bond?
Oh, Alice, the OH bond. Yes, you did lack yes, but you made, there was the same number of OH bonds broken and formed. So you don't need to know what they are. I think you made 2 and you broke 2. So it was a wash. I see what you're asking. Yes, there were also OH bonds, but they were the same number broken and formed. So if you would have written it all out, you could have canceled those out. Okay. Fantastic, guys. See you all on Monday.